Hello, my name is Marina. I'm a PhD student in computational chemistry from University of Novi Sad. A little bit later, you will hear from my colleague Sepinoud. In this talk, we want to discuss potential approach to combine molecular dynamic simulations with artificial intelligence for nanoparticle design in cancer treatment. Cancer treatment has come a long way. However, existing treatments, such as chemotherapy or radiotherapy, although effective, still have major side effects. And this is because they affect not only the cancer cells, but the other healthy cells as well. The field of nanomedicine has emerged as a possible alternative strategy. Use of nanoparticles as carriers for drugs have been shown to improve efficacy and also to reduce side effects by improving site-specific targeting, controlled release, by extending compounds' blood circulation time, and it has also shown the potential to modulate both pharmacokinetic and pharmacodynamic profiles of drugs. And although this is a promising approach, it has its own obstacles. To design new and effective nanomedicine, we need thorough understanding of its physicochemical properties and behavior in biological environment. However, it's often difficult and sometimes even impossible to obtain this kind of information experimentally. Additionally, there are other variables that we have to take into consideration before designing a nanoparticle. For example, we need to choose which nanoparticles we want to use, organic or inorganic, what would be the size of those nanoparticles, charge, which molecules are we going to functionalize this nanoparticle with, which drugs we are going to use. So really, we cannot know in advance if that design will be effective or not. We can start with one design, then systematically vary the composition, test it, observe its effects, and finally determine the best design. But doing that experimentally can be time-consuming and quite expensive. One way to overcome these issues is to use computational methods, and one of the most frequently used tools is molecular dynamics. It is frequently used to investigate structure, dynamics, energetics of different molecules. And by running these kind of simulations, we can get detailed information about the properties which could be quite difficult to obtain experimentally. So, how can molecular dynamics help in the design of new nanomedicine? Comparing to experimental approach, systematic variation of composition can be done much easier, faster, and cheaper. And the idea is, if we do this preliminary screening computationally, we can make life of experimentalists at least a little bit easier. And overall, we can accelerate the whole process. How do we investigate structural variations and their influence on the behavior of nanomedicines? We start by building different systems, different nanomedicines that we want to simulate. In EVO Nano project, we use gold nanoparticles, which are functionalized with two different types of ligands. One, which carries anti-cancer drug, and the background ligand, which can have different functions. For example, if anti-cancer drug is hydrophobic, we can use background ligands which are hydrophilic in order to increase the solubility. We build these components separately and then assemble them together. We can choose, for example, different ratios of these ligands that we want to simulate. Then we can move forward and start building variations of this system. We can, for example, switch type of nanoparticles we use, we can switch its size, we can switch ratio of the ligands, or we can switch the ligands themselves. After we prepared our nanomedicines, we start running simulations in biologically equivalent environment so we can see how these structural changes we made affect nanomedicine behavior. After the simulations are done, we analyze the results to see which chemical modifications are favorable, and in the end we can forward most efficient designs to experimental groups. Although this approach is promising, it can always be improved. One of the issues here that should be addressed is that the state space of simulation inputs could be dramatically large. There are a lot of different parameters that should be changed, and we should also test different combinations of these parameters, so in the end it's not really feasible to run simulations for all possible variations, although that would be ideal. Moreover, despite requiring less time than performing this whole process experimentally, it still takes a lot of time. It takes time to build and to prepare systems, then we need time to run the simulations, time to analyze the results, and if we can make this process faster, that would be great. There is always a question of computational resources. Computational costs can be quite high. So one way to improve on this is to combine these simulations with artificial intelligence. And now I will let Sepinoud talk more about the AI.
As it was mentioned in the first part of the presentation, in this project we are dealing with a unique, complex, and multi-featured problem, which in turn requires sophisticated approaches to correctly identify a solution. It is also worth keeping in mind that the time feature is another important aspect, as we are dealing with a multi-step problem. Also, relying on simulations as the only tool is not realistic, as we are dealing with a largest data space that requires long simulation times and huge computational resources. Due to substantial perceived costs, it's also not practical to rely on in-lab experiments. An approach that has proven successful in dealing with similar complex problems is deep learning. Deep learning refers to a family of machine learning techniques whose models extract important features by iteratively transforming the data. In simple words, it means that the model goes deeper and deeper toward meaningful patterns in the dataset with each transformation. Deep learning models have certain advantages compared to more traditional ones. One of them is that the deep learning models are easily adaptive, which means that these models pass data directly to the network and have a good performance, unlike other methods where the best features are carefully selected to pass over to the algorithm. And this is very good and very important because these type of architectures could be adapted to different domains easily, which gives a higher performance in a shorter period of time. Deep learning models also have greater accuracy. They themselves learn to extract features from the dataset, which is very important, and the only way to increase the accuracy is to input more data, and the accuracy attained is much higher in these methods. Another strong point of deep learning models is feature selection. Because deep learning models try to learn features from the data in an incremental manner, they eliminate the need for an involved feature extraction step, since this step is included within the training itself. However, this is not always rosy and beautiful. The high accuracy deriving from an increased model complexity often comes at the price of loss of interpretability, which means that many of these models behave as black boxes and fail to provide explanation on their predictions. While in certain application fields it's not such a big deal, in high-risk domains like what we are dealing with here, healthcare, people's lives, it is crucial to build the trust in a model and being able to understand its behaviors and its decisions. A key requirement for an effective AI model is the ability to generalize, and this is something that's not necessarily there always, which is to perform well on samples that has not been seen in the training phase. And to establish the generalization abilities of a model, it is often not enough to examine only its validation performance. So what we decided to follow as an approach is include an explainable AI aspect to the solution we are proposing here. Like AI itself, explainable AI isn't a new domain of research. It has been around for quite a while, but recent advances in theory and applications of AI have put new urgency behind efforts to explain it. Explainable AI is about explaining why and how an AI model came to a decision, which what it means to explain a model can vary widely depending on the user's role and level of sophistication, as well as a specific constraints of given application environment. For example, Consider a developer creating an AI model. This user might prefer explanations that describes the inner working of the model to facilitate debugging. On the other hand, you consider a lay user who is examining the fairness of an AI model, who might prefer explanations that relate its input to its output. In our specific projects, we are interested in three different things. First, we would like to know what the important input features are in designing the optimal nanoparticles. Also, we would like to know what are the optimal value ranges for those features, and finally, how the deep learning model have come to those conclusions so that we could replicate the machine's thought process. In general, explainable AI approaches could be categorized in three different classes. The first one is it could be applied before starting the modeling, which is the pre-modeling explainability. It could be also applied during the modeling phase, which is explainable modeling, and the one that we and many other people are interested in is post-modeling explainability. In short, pre-modeling explainability is a collection of diverse methods with a common goal, which is to gain a better understanding of the dataset used for model development. Explainable modeling is basically trying to avoid the black box altogether by developing a model that is by design explainable. This would inherently limit our choice of architecture. That is why we are specifically interested in post-modeling explainability, which led us to both use the advantages of deep learning models and describe the decision-making process. And as I already mentioned, this is probably the most popular explainable approach, the post-modeling explainability. And as such, there's a growing body of literature targeting this area. We specifically would focus our efforts in three different mechanisms. The first one is the backward propagation mechanism. And in this mechanism, the resultant explanations are often importance scores in terms of input features of the model. To obtain these scores, the backward propagation mechanism starts with a layer that is producing the given target and estimates the contribution of neurons in the layer previous to that target. The process is repeated layer by layer until the contribution of input layer features are obtained. The second mechanism that we have in mind to apply is the proxy mechanism, which is the explanation, which is to find a model that imitates the original model with a simpler and more comparable performance. This mechanism is often applied to replace complex deep neural networks with more explainable models such as decision trees or decision rules that faithfully represent a deep network model. And finally, the last approach that we are interested in is the activation optimization mechanism, which is often used to generate explanations of the inner working of deep network models. Its explanations are obtained by searching for an input pattern that produces either maximum or minimum response for an inner component of the model as a target. This search problem can in turn be formulated as an optimization problem and solved using a gradient-based approach. The final important step in this project that we would like to perform as a last step is, of course, the validation phase. And for validation, we hope to be able to provide a detailed guideline on how to design a preferable set of nanoparticles. When we have these guidelines and we have, in theory, designed our nanoparticles, we could feed these nanoparticle designs to be tested first as the input of the simulation in a simulation environment, and then we could build and test them through in-lab experiments. As we already mentioned, this is an ongoing project, and we are definitely not in the more advanced steps of the project, and we are in the early stages. So we would be happy to answer any questions related to what we discussed up to now.